Professor Y.Qi of University of Virginia will deliver his last lecture of his series.
All right. Thank you for the introduction, and thank you again for the invitation and everybody for making it to the last one. In the last lecture, I'll try to sketch a little bit of, go back to the motivation that I mentioned during the first lecture, that the goal is to construct topological field theories, and we want to categorify some of the key ingredients in constructing Witten-Rush thinking TRIF 3D TQFT. So this is the motivation. So as we have heard from Chang-Hei's talk yesterday, one key ingredient in Witten-Rush thinking TRIF 3D TQFT is the fusion product, or what you assign to a pair of pens or a sphere with 3 punctures. That's the underlying manifold is very easy, but this is the basic building block for what you assign to two-dimensional manifolds. So in quantum group, the representation theory of a quantum group at roots of unity, there is a parallel construction of this fusion product, which is slightly easier than I think the affine picture, but they are equivalent under Kac-Lustig equivalence. But this is a more highbrow approach. But I'll just stick with quantum groups at roots of unity. How you do it is you just take quantum group at roots of unity, takes so-called tilting modules. So it's a special class of representation contained as direct summands of tensor products of fundamental representations, and take their tensor product and similar as we have seen yesterday, you take threefold tensor product V lambda, V mu. Tilting modules are also parameterized by highest weights, lambda, mu, and T nu star, and compute the invariants inside them. So this is how you can do that from quantum groups perspective. So we want to be able to categorify this. So the entire picture to a 4-dimensional theory. So what we want to do is, as the first step, let's try to categorify tensor products of quantum group representations. And I'll give you how this is the first step, how we can do this, at least for UQSO2 at a p-th root of unity. So we want to categorify tensor product of certain representations called Y modules at a p-th root of unity. Okay? And so Y modules are not very easy to understand. So for at generic Q values, or you can do this over an integral lattice over ZQQ inverse. So let me give you a brief introduction if you haven't taken like representation theory of V algebras 101 before. So this is what do Y modules look like. So Y modules are parameterized by highest weights for SL2. So the highest weight is just a natural number, and it has a very concrete algebraic construction. All you have to do is you put L plus 1 vectors together. Well, you pick an L plus 1 dimensional vector space. Let's list all the basis vectors as dots. So these dots indicate their basis vectors for this L plus 1 dimensional vector space. And these numbers indicate how the K operator acts on this basis vector. Then E and F, just E up to a scalar, E just raises the corresponding basis vector to higher and higher weights, and F lowers the corresponding basis vector with to lower and lower weights. So this is up to rescaling. So roughly speaking, EI sends one of these vectors to quantum I plus 1 to where if this is I, quantum I plus 1 copies of VI plus 1, etc. Okay? Is this all right? So this simple algebraic picture actually has a very natural geometric construction that I don't think many people probably know, but just didn't write it down carefully. So I'll be borrowing the picture from Franco Kavanov construction. So this geometric description is, well, you want to lift the vector spaces to some categories. So these vectors we have seen will become the basis vector of the corresponding Grothendieck group of that category. So natural choice of these categories is if you fix an L, just choose the Grassmannians of K-planes in L-dimensional space. So this is going to be an algebraic variety. You can think of this as GLL quotient, the parabolic subgroup of size K times L minus K. And so this category, this variety is acted on by the group GL of L. So the action is transitive. So we consider constant sheaves of locally constant sheaves on the entire variety. So this is a very or G equivalent sheaves on this variety. So this is a very nice category, a very easy to understand. And on this category, there are functors for between different K and between different K values. Sorry, constructible sheaves, sheaves of locally constant. Yeah. So, but here it's we required to be GOL constructible, so it's essentially constant along the on everything on the entire variety. So you have two projection maps coming from the incidence variety of GLK and between two neighboring Grassmannians. Those are K planes contain K plus minus 1 planes contained in K. So you can along these planes you can do push forward and pull back. So you naturally have functors between these two categories, neighboring categories. And if you want, this is actually an easy exercise to check that this data of using bijunction of E and F, maybe there's secretly up to some gradient shift. This defines a weak version of categorical SO2 action on these categories. So this is a geometric categorification of the irreducible representation of wild module. Okay, so I want to translate this slightly into a stronger version of categorical SO2 action, and furthermore, be slightly more algebraic. And how do you do that? So earlier we have said sheaves on these varieties can be identified as let's say DG modules over some generating sheaves of these categories. The generating sheaves are just the constant sheaf. Everything is a module over the constant sheaf. So the endomorphism algebra of the constant sheaf on these varieties are just cohomology rings with a natural differential structure. And these cohomology rings are all concentrated in even degrees, so they're all formal. So therefore, algebraically, these sheaf categories are just DG modules, or really just modules over the cohomology ring of K planes in L space. Okay, so and this gives us an algebraic way of describing this categorification. So you can safely replace this. This is just a commutative finite dimensional Frobenius algebra, and this cohomology of this instance variety is just going to be a bimodule over this guy and this guy. So you can use induction and restriction along these bimodules to give you the same categorification. Okay, so that's the geometric picture. And both this very easy geometric picture affords vast generalizations. So in ADE, finite ADE types, this is done by Nakajima quiver varieties. These are just the zero sections in Nakajima quiver varieties. So if you take coordinate bundles of these varieties, and you get there are special cases of quiver varieties. And beyond ADE, in arbitrary finite type, this is done by taking cyclotomic KOR quotients as proven by Kang and Kashiwara. So this is, I'll use the later approach and try to connect it to the geometric picture and see why this is indeed the case, at least in the case of SO2. So as we have seen, these categories, VL is a highest weight categorification, so categorifies a highest weight representation. So essentially all these weight spaces VL of K. So this is a weight space or weight category. This V of K is the modules over or sheaves over K planes in, remember this is sheaves of K plane Grassmannian in L space, is derived Morita equivalent to just you apply this functor F to the highest weight category, which is this is in this case is just K vector spaces, and apply the lowering functor to it, and you would get this category. And how do you describe this category more carefully? And last time we have introduced this important algebra that acts on these functors. So this is, in some sense, the modern sense of categorification is you really need to study not just functors, but natural transformations between functors. And this, once you have this more refined information that tells you how to construct these categories explicitly. So on this f to the kth power, we have seen that the functor we described in yesterday's lecture, there is a neo-Heck algebra action on it. I have ignored the arrows, up or down arrows, so it doesn't matter that much. But let's just fix one orientation and ignore that, and remember that the algebra that acts on the composition functors is there are dots representing the cohomology class of the line bundles, and there are crossings representing the divided difference operator on cohomology classes. And they satisfy the neo-Heck relations, as we have seen from yesterday's lecture. And furthermore, because of this concrete realization, how this algebra acts on these functors, and this functor, remember the first line represents endomorphism on the choice of line inside CL. So that's essentially the first term class on this line. When you raise it to the nth power, it will be 0. So therefore, you have to impose one further condition called the cyclotomic relation, and this category is the neo-Heck algebra modulo this relation gives you really an algebraic realization of this categorification. So this neo-Heck graded modules over neo-Heck algebra categorifies this irreducible representation V of L. Okay, and it's using the discussion we just have shown you. It's not very difficult to verify that this algebra is actually Morita equivalent to its center, which is the cohomology ring of the Grassmannian. So their representation theory are equivalent. NHK without L, this is the neo-Heck algebra without this relation we have drawn yesterday. Just these are all natural transformations between F to the K, and then you impose this condition L. This is the cyclotomic neo-Heck algebra. So this entire picture is generalized to arbitrary Kovanov-Lauda-Rookie algebras, and if you are given a highest weight of the corresponding type, the corresponding cyclotomic quotient categorifies the Y.Qi hat representation of that highest weight. This is the theorem of Kang and Kashwara. And so,
use the center fed here.
What's that?
Center is the fed.
In that case, center is in AD type. It's isomorphic to cohomology of quiver varieties. Yeah. Questions? All right. So now I want to describe. This is a categorification of just a single representation of highest weight L, and we want to use this to help us construct tensor product categorification. So how do we extend this categorical action? So one way is, well, if you have taken basic representation theory, you know that V of L sits inside for SO2 as a sub-representation V K tensor V maybe R L minus R. So this, and there's natural inclusion map and natural projection map. So what I want to claim is that once you know the categorical action, once you categorify the picture here, secretly you already know something that's know some categorification model for this representation. So what we want to do is we want to extend the earlier construction. So let's summarize or axiomatize the picture we have seen. So we have seen a family of symmetric Frobenius algebras coming from cohomology rings of equivarieties, or these are actual cyclotomic quotients of KR algebras. And you have a bunch of modules over this ring. So this is coming from some natural right modules defined over AK. So we just define the corresponding B side of the algebra is just the endomorphism algebra of M over A. So that this M is going to be a bimodule, a BA bimodule over these rings. Okay, and also suppose we have constructed categorical actions on this AK, and then this AK A and B side are related by this natural. There's essentially one way or two ways to define these functors. Is you can take the tensor product to give you a functor from A module side to B module side, and its corresponding adjoint from B module side to A module side. So this is the Hom. So okay, so they're naturally related by these two functors. So we have already constructed actions on the A module side. So this is there are functors relating A module to A module. So it's given by again by tensor product with some bimodule AJ AI bimodule EIJ, which I call. And so this picture, well, this is saying that when you do this concatenation of functors, you get the functors. So this is slightly more general than the SO2 part, but this is the most general picture you can imagine for this abelian version of categorical action. So you have this diagram, and this A module side is related to the B module side by the natural functors we have constructed, this S functor and J functor. And so it's natural to ask yourself, does the categorical action here extend to the B module action side? Okay, so this is, well, let's just force ourselves to define this on the B module side, the composition functors. So there's only one way to compose. So this J composed with E composed with S. So you get these corresponding functors. Okay, you want this relation to still hold. This the composition of EIJ with EJK is isomorphic as functors to EIK to extend to the prime side. Well, the most natural condition is as you can see for this to hold, it's better. You'd better require this composition functor here to be the identity functor. Okay, so if you have this composed with that is the identity functor, then you naturally get this for free. Okay, so what's this condition? Si composed with Ji is identity by definition. So this, when you apply this functor to the free module AI, so this is AI, the right hand side applied to the free module is AI. When you put it, apply the left hand side to AI, Ji is M tensor with AI does nothing, so it's just Mi. And Si is Hom of Mi into Mi, so therefore you get endomorphism ring. Okay, so therefore to require this condition, that's equivalent to saying that you have the double centralizer property on the module M, which is double centralizer property is a very prominent thing to require in representation theory. Okay, so if you have the double centralizer property, this action will extend to the B module side. Okay, so this is an overly simplified model that I will try to modify a little bit later, but now just remember that once you have double centralizer property, there is such a categorical extension. So this double centralizer property, after we proved this requirement, I found that this is actually defined in, discussed in Curtis and Reiner's classical textbook in representation theory many years ago in the 1960s. So, but let's just recall this theorem. So if you have, when does the double centralizer property hold on the right A module M? So if A is a Frobenius algebra, as in our case, M is a faithful A module, then this always satisfies the double centralizer property. This is actually if and only if condition. So it's the if and only one part is very trivial because they have double centralizer property will tell you AB both acts faithfully on M, but the other side is if A acts faithfully on this module M and A is Frobenius, then they automatically satisfy the double centralizer property. Faithful just means non-zero elements act non-zeroly. So the action of A into the endomorphism ring of M over K is injective. Yeah. Or different elements act differently on M. Okay. Any questions? So I was a little bit surprised. This result seems to be pretty basic and fundamental. So but it's not taught in modern representation theory books. It's not included, but it's included in Curtis and Reiner's classical book. So I really like this. And once you have the double centralizer property, this module M is very nice over the B side. This module is always projective injective over B. What's that? M already exists. We assume that it exists. Yeah. For instance, you can always take M to be A itself. So there's always a free, but usually M will be bigger than just A. Yeah, so for instance, the usual Morita equivalence is a special case of this when M is just direct sums of some free modules, a projective generator of A modules, then this includes the classical Morita equivalence context as a special case. Anyways, so furthermore, this M is a projective injective module over B, so that this functor Ham of B out of M from B side to A side is exact, and it's actually fully faithful on projective B modules. So this context, this entire context, is very reminiscent of what we have seen if you have studied regular category O of classical Lie algebras. This is what the Soergel functor does. So that's why we call this the generalized Soergel functor in this context. Okay, so any questions? What?
Yeah, you know, by definition that as it's represented by some functor, the functor will be a quotient functor.
Yeah. Projective.
The kernel of this functor, the special functor.
Yeah.
There's some category generated by projective functors.
Yeah. Exactly. It's really entirely parallel to the Soergel story. Yes. Yeah. This map later here, we'll build up the this tensor product categorification as certain extension of B modules. So you have to pick carefully what kind of M you use to construct that. Okay. All right. So again, I think every lecture of mine will contain a proof of some result, because this result is very fundamental. I think I'll give you the proof due to Curtis and Reiner. So let's sketch a proof for the benefits of graduate students. Without loss of generality, I'll assume that A is basic. So if A is not a basic algebra, that means that the simple modules are always one-dimensional. over the ground field. If it's not a basic, you can reduce it to the basic case by Morita equivalence. It's not very difficult. So how do we prove it? Huh? Basic is when you your simple modules are just one-dimensional. So yeah, usually if you have a non-basic algebra, you can decompose the left regular module into direct sum of the projectives. And if the projectives appear with multiplicity, you just get rid of the multiplicity and consider endomorphism algebra of those projectives. That would be Morita equivalent to A. Okay, so first we show that if you have a faithful module, actually this faithful module must be of the form it's A direct sum some other A module. Okay, as a right A module. So it's not very difficult to. So faithful if and only if essentially it's if and only if this condition holds. This is because A is Frobenius. And why this is the case? Well, if A is, let's write A as a direct sum of projectives, indecomposable projectives. So with multiplicity 1, that's why it's basic. Well, let's. I don't know if everybody knows the Soergel notation. Soergel just means the maximal, not max, the simple submodules sitting inside A. Each simple submodule is contained in one of the indecomposable projectives. And because we're in the Frobenius situation, these projectives are also injectives. So these PIs are the injective covers of the corresponding Soergels of simple submodules sitting in A. So the Soergel will be generated by some element xi, A times xi, and A times xi is contained in PI. This okay? So PI is the injective cover of xi. But because of the faithfulness assumption, xi will act non-zeroly on M. So it doesn't annihilate everything. So you can find something that's not killed by xi. It's okay? So therefore, if you think about this xi times mi and left act by M, by A, well, this is gonna be just a copy of the Soergel because it's a simple module. A times xi is a simple left module. So therefore, the simple left module extends embeds in M, and this is the injective cover. So therefore, you have a natural embedding of the injective into M, just using basic homological algebra. So therefore this PI will appear as a direct summand inside M, and you can do this for each summand PI here. So therefore, A has to appear as a direct summand. Yeah. Did I switch left and right? Sorry, I might have switched left and right. Yeah. So otherwise. Yeah, earlier I said M was right module, so maybe xi should be on the on left. Doesn't matter. Is this okay? All right. So once you have a decomposition of M into A direct sum N, we can formally write the endomorphism algebra of A as a matrix form. So it's endomorphism of the A component, endomorphism of M component, and maps that interchange A and N. But this left corner is just as a module, just isomorphic to N. This okay? So, well, now if you have, we want to show the double centralizer property. That means if X is a bilinear map, we want to show that it coincides with left multiplication by some A. Okay? But X is a bilinear, so that means it commutes with the natural idempotence 1, 0 here or 0, 1 here. So 1, 0 here is the projection of onto the A component and including back into M. And likewise, this is projection of M projecting onto N and including it back. So commuting with these two idempotents just means that X act component-wise on A and N. So must act on A individually, act on N individually. But X acting on A individually means that there is a left multiplication. There is an element A0 such that the effect of X is left multiplication by A0. Okay, and then we want to show that the action of X on the N component is also left multiplication by A0. And to do this, it's not difficult because the upper left corner is isomorphic to N. So you can write arbitrary elements N of this form as the element 1 multiplied by this matrix. And remember, this matrix is in B, so X commutes with the action of this matrix. So therefore, you see that X acting on N is the same as X acting on 0N, and X acting on this, using this action. And on this element, we have already shown that X acts by left multiplication by A0. So therefore, you get that this is get the desired result. Okay, just some very basic ring theory. You can show that this is so anything commuting with the B action comes from A. Okay. So this result is actually quite useful. For instance, in Soergel-like duality in arbitrary characteristic, you can use that to show Schur algebra is satisfy this property. Okay. All right. Next, we want to show that it's projective injective. So it's very easy to show that, well, its projective is very easy because M is isomorphic to Hom of A into M over A. And A is the direct summand of M. So therefore, it's a direct summand in this guy, and it's projective. And similarly, to show that it's injective, I want to show you that it's actually M is isomorphic to a dual module of a projective. So to do this, we need to use that A is Frobenius so that A is actually isomorphic to its dual as a bimodule. And so we can write M as M tensor over A of A, but we're identifying A with its vector space dual. And so the dual is, the isomorphism between A and A dual is given by the Frobenius pairing. And so let's just, for now, put a double vector space dual over here and use tensor Hom adjunction to show you that this is this is one dual, a dual. Okay, now you can use tensor Hom adjunction to show that this is Hom of A of M into A dual. But this A again is a summand in M. So this is just as in here. So this is a projective module, and it's a projective module, a right projective module dual to become a left. So it's a left. I think I switched right and left badly in here, messed up. So, but in any case, the vector space dual of a projective module becomes an injective module. Okay. Any questions? And sorry. Yeah, finite dimensional algebra, finite Frobenius algebras. A is always a finite dimensional Frobenius algebra. Think of it as cohomology ring of quiver varieties or Grossmanians or things, or cyclotomic quotients of KR algebras. Yeah, you have to come up with some useful module M over cyclotomic KR algebra. Okay, but such choices are already provided in many other works done by for instance, Hu and Mathis and Ben Webster. And okay, so as a consequence, you can show that no matter what this module you pick, the centers of A and B are equal, so they all agree with the center of A, which is in the interesting cases are cohomology rings of quiver varieties. So here's an exercise. So using this theorem, you easily deduce that in this categorical action on the A module side, if you have all Frobenius algebras and faithful modules over them, then the categorical representation on the A module side extend to a categorical representation on the B module side. This okay? I hope this is clear, because double centralizer property guarantees that the earlier extensions will be identity. So if I go back to this diagram, that's the proof of these compositions will always be identity. So what you have shown on categorical action side will extend to this side.
Usually equivalence is the Voigt equivalent, up to Voigt equivalent.
Usually A and B are not Morita equivalent in this case. Yeah. All right. All right. So I'm slightly lying a little bit. These functors J and S, although they're the most natural functors, but their effect on projective modules are sometimes more difficult to analyze. So this is closely related to if you define actions geometrically, sometimes you have to do a lower shriek or lower star, and these two different versions will have different effects. So I want to slightly modify the picture a little bit. We want, instead of the functors, if you just define it naively as I just described, this naturally extended functors epsilon ij prime will rarely send projective modules to projective modules. So if you don't do that, if you are in this situation, it's hard to know what happens on the Grothendieck group level. So therefore, we simplify this situation by considering this module, which is mi check, behaves slightly nicer than mi. So mi check, as we have seen, is by definition is the dual module of m into B, and earlier we have seen that m is going to be always projective injective. So this Hom dualization doesn't damage m too much. It doesn't lose too much homological information of m. So therefore, what we really want is a right adjoint functor to the Soergel functor. So this is what I call I of I instead of J of I. So this is of this module, a dual module into from A module side to B module side. It's this functor will usually behave much better, but under the double centralizer property. So if you know that A and B satisfy double centralizer property on M, then this you can easily show as an exercise. In module theory, you can show that this module mi check is isomorphic to just the vector space dual of mi. So you're not losing any information. Using this module, this functor behaves much better for the study of projective modules. It still satisfies the double centralizer property, and if you define similarly as this functor, instead of using the functor j's I wrote down earlier, you use i's. You can still show that if this collection of original functors preserve the additive envelope of this collection of modules. Okay, so now we have a stronger assumption that it will send mi to a direct sum of direct sum will preserve this additive envelope of mi star. Then these functors will extend the categorical action, preserving projective modules. So we send projective B modules to projective B modules. So because we're considering later for categorification, we want to analyze the effect of these functors on K group. So this is going to be the easiest case. If it sends projectives to projectives, you don't have to do resolutions of modules anymore. So this will be the easier. All right. So now let me provide you some concrete cases where these modules are actually naturally provided in previous work of Hu and Mathis. So by connecting the earlier story of what we have done for cyclotomic neo-Hecke algebra, and we have already shown you that there are functors E and F acting on cyclotomic neo-Hecke coming from induction and restriction, and so we need to find some collection of faithful neo-Hecke modules that are preserved under this corresponding functors. So the modules are already actually naturally provided, or if you study Schubert calculus, I think many people already knew that's how to construct such collection of modules. So I'll be using a language in Hu and Matthias' work. So fix the highest weight. A neo-Hecke partition, lambda of weight k, is just a decomposition of L into ones and zero boxes or empty sets, such that the total number of ones or total number of boxes is equal to k. Okay, so this partition naturally parameterizes the Schubert number of Schubert cells in k planes in L space. So this is a natural combinatorial gadget to consider. So this set of neo-Hecke partitions is in one-one bijections with Young diagrams of size L minus k times k, and I'm borrowing Hu and Matthias language. So for instance, this is when k equals 1 and arbitrary L, you have these partitions. So translating into Young diagrams, it's of this form. And to such a partition, you can define a module as follows. So if you have a partition like this, where the boxes are in position J1 up through JL, remember this is we're thinking of this as combinatorics of neo-Hecke algebra of k strands with cyclotomic condition L. So you have on k strands you have these variables y1 through yk, the dots. So if your positions are the boxes are in here, you just consider this monomial. So this is this comes from you do corresponding to this partition, you do partial resolution of the Schubert cell. So the corresponding top cohomology class is this guy. So summing over all such partitions, this right module, this module is the desired module M we have been thinking about. So this is the right neo-Hecke module, and we define the Quiver-Schur algebra as the endomorphism ring of this module. Okay, so this is Quiver-Schur algebra will be the B module side of what we have considered. So just as a concrete example, continued with last one. So if when k equals 1, this is neo-Hecke neo-Hecke algebra of size 1 strand is very easy. Just truncate a polynomial ring, ky quotient y to the nth power, and putting so this in the earlier combinatorics where the box appears, you just take the corresponding y to some power. So you can easily list all these modules. What are these modules? So this y to the lambda times L is just y to the L minus I. So it's not necessarily simple, but you see that when I equals L, you get the module generated by 1. So this is always a faithful. It's just going to be this free module. So it's always a faithful module. So the endomorphism ring between these modules is the type A zigzag algebra that has, you can map one module to include one of these into higher powers, or project into that, and project is 1 to 1 is 0, and any of the loops are equal as a Quiver algebra. So this is this Quiver algebra appeared everywhere in categorification or in representation theory, because it's actually a special case of Quiver-Schur algebra. Okay. Any questions? All right. So a key lemma already proved in Hu and Matthias' work is that this is a faithful module, and it's actually self-dual. So it's the vector space dual is isomorphic to itself as, and so it's it fits perfectly into our framework. So consequently, just now putting the earlier framework into this picture, the functors E and F, all you have to check is that the functor preserves the additive envelope of this this collection of modules. Then the induced functors, I think I should have written double prime, E double prime, F double prime on this Quiver-Schur algebra category, categorifies the tensor product representation of C2 tensor L. So this is here, instead of VL, this is V1 tensor V1 L times. Same picture. The V1 is the two-dimensional representation of. Sorry? SKL. SKL is the Quiver-Schur algebra endomorphism ring of this module. Okay.
This is called the so-called Schur configuration.
Yeah, this is so-called Quiver-Schur algebra. This also generalizes to.
The quantum equation is Schur quantization.
No, it's not quite Schur quantization. But this algebras appear in the study of geometric representation theory prominently because this algebra is described. So earlier we have described Neal-Heck algebra describes sheaves over G constructible sheaves over this variety Grassmannian, but here this algebra, because of its construction, you're resolving Schubert cells. This describes sheaves supported on each Schubert cell. So the natural category is B constructible sheaves on Grassmannian G of K-plane in L space. And so the geometric functors are still the same functors, and it induces the category. So another geometric realization of this categorification is taking B constructible sheaves on this category. B is the Borel subgroup of GLL. Hypertriangular. Okay, questions? Yeah. Yeah, Neal-Heck algebra act on this functors. Part of Neal-Heck algebra. Sorry, what's your question again? Co-multiplication. Yeah. It's not easy to see how the co-multiplication on SO2. This just realizes this tensor product categorification of representations, not on the quantum group Y.Qi It doesn't give you a realization of. Yeah, actually, this is a very deep question. I think Rukia proposed the solution to how do you write co-multiplication on categorified SO2 back in 2008. He still hasn't written it up. I think he has done hundreds of pages of computations on these categorification results, but it's not written anywhere how the co-multiplication is.
So you mean this is not the representation of the algebra UQSL?
It's just as a module over UQSO2. You construct the tensor. Oh, sorry. Ooh, what happened? Yeah, you just directly construct it as a representation of UQSO2. You never go through the tensor product the co-multiplication. Yeah, realizing the if you realize the tensor product, the co-multiplication on categorified quantum group, you would be answering the question raised by Crane and Frankel in their original paper. So what is a half category in? So that's still unknown. All right. So now I want to combine the previous generic categorification story with the theme of my lectures. So it's at prime roots of unity. And by now you're probably familiar. What we do is we enrich everything with p derivation in the story. So what happens is in the previous lecture, the Neal-Heck algebra as part of the two category inherits a p differential defined as follows. So we just need this generators. And notice that this differential preserves the ideal of the cyclotomic relation. Because d of Lth power is L times L to the first, L plus first power. So it preserves this cyclotomic relation. So therefore, it extends naturally to the cyclotomic Neal-Heck algebra as a p derivation. So the PDG category, when you take the correct version of derived category, compact derived category, it categorifies really the wild module at a prime root of unity. So it's specializes Q to a pth root of unity. Okay, and now again we can translate this into the PDG setting. You want the functors to preserve the additive envelope, but as we have seen from yesterday's lecture, additive envelope of modules is you just allow direct sums of them and direct summons inside them. So, but direct sums and direct summons are really rare in triangulated category. So instead, you want this functors to preserve the filtered envelope, which means that modules that have a filtration whose subquotients are in the additive envelope. And once you forget the p differential, the filtration becomes a direct sum decomposition. So this is a most naive generalization of most obvious or naive generalization of the additive envelope story in the PDG setting, and it works pretty well. So if this functors preserve the filtered envelope, then the extended functors extends the categorical action to the B side. So furthermore, it sends instead of projective in the derived setting, you replace projectives by cofibrant modules in some model structure. So it sends cofibrant to cofibrant modules. And again, the same story at generic Q case holds. So the functors we have utilized in their divided powers. Actually, in this case, I never really introduced divided powers of small quantum group. So this is the subtlety of between small quantum group and Lustig's version of quantum group specializing the big quantum group to root of unity. So I don't want to go into the details. But there are various versions of quantum group at roots of unity. Here we really need the Lustig's big quantum group. This is actually where tilting modules are defined. The half algebras where tilting modules are defined for. So this functors of E and F and their corresponding divided powers will preserve the filtered envelope and extends the categorical action from the A module side to B module side, from Neal-Heck side to the Schur algebra side. So when you pass to derived categories, this action categorifies the quantum SO2 action at a prime root of unity. Is this okay? So I'm hiding a lot of details in the proof, but I hope I convinced you that it's natural. It's a natural generalization of the abelian case. So for instance, again, continuing with our earlier example, you can calculate how the differential acts on the Quiver-Schur algebra side. For the Quiver-Schur algebra side, we have drawn earlier for this quiver, for this S1 of L is very easy. So to a right arrow, it just appends a loop to the right pointing arrow appends a loop centered at that vertex. and to the left pointing arrow, it just annihilates it. And you can easily show that the PDG Grothendieck group is of the correct size. It's the weight space of V1 tensor L of the second highest weight. And this quiver algebra was analyzed by Josh Susan and myself in an earlier paper, just as a combinatorial model. And we have showed that there is a categorical braid group action on the derived category. This braid group action actually categorifies the Biot representation of SO2 at a prime root of unity. So in our continuing work, we'll show that this braid group action extends to the quiver-Schur algebra side. This is part of the categorifying fusion product. You want the S. There's so-called SNT matrices, and to build the SNT matrices, you need this braid group action.
You mean representation of braid group?
Yeah. Biot representation. Sorry. BR of n. Sorry. L is L should be n in here. Sorry, my apologies. I'll send the corrected notes to Y.Qi. So anyway, more questions, comments? All right. So, and actually this algebra, you can define it in this algebraic fashion, and it's actually isomorphic to a block in Webster algebra. So you can actually draw them diagrammatically. So if you compare the combinatorics, the quiver-Schur algebra is isomorphic to some idempotent truncation of the Webster algebra, and it's also PDG-Morita equivalent to the Webster algebra. You can draw this as in the Webster style diagram like this. You put walls between weights. So each of these walls represents the highest weight of V1, and you allow Neal-Heck diagrams in between, and very similar to what you have seen for cyclotomic Neal-Heck algebra. This you impose the natural conditions on these diagrams gives you the corresponding Webster algebra. So quiver-Schur algebra also admits this similar diagrammatic description. All right, finally, before we quit, I just want to mention there are many further questions we need to answer to continue this program. So this construction naturally leads to some natural generalizations to arbitrary tensor product of arbitrary highest weight. They all sit inside V of R1 plus all the way to V of RD. So what you do is similarly as before, you define this multi-partitions as before, but put red lines in between. And there's a natural collection of truncated polynomial modules over a Neal-Heck ring, and you consider the truncated quiver-Schur algebra. So as a conjecture, in the generic case, this is true, but so to prove this conjecture in the PDG setting, you need more tools to actually compute the PDG Grothendieck group. So this desired data should categorify the tensor product representation at the prime root of unity. Okay, so this conjecture, as we have shown, this collection of algebras also describes the parabolic constructible sheaves over Grassmannians. So what we have shown is when the parabolic is a Borel, this is true, and when all Ri's are 1, this is true. Okay, and when you have only 2 tensor factors, this is also true. All right, that's all I have for the lecture series, and thank you for your attention.